Hello and welcome. My name is Mugdo Day, and in this video, we'll be diving into Unit 5 of our chemistry course for January 2025. This unit covers some of the most essential concepts in modern chemistry, and it's designed to strengthen your understanding and prepare you for upcoming assessments. Whether you're reviewing for an exam or aiming to solidify your grasp on the topic, this walkthrough will guide you step by step through the key ideas, examples, and problem-solving techniques you need to succeed. So let's get started without any further ado. Okay, so the first question here says, which species can act as a ligand in the formation of a complex ion? Okay, a ligand is a species which tends to have a lone pair of electrons. So if it does not have a lone pair of electrons itself, it won't be able to donate it to the central transition metal ion. So we now know here that nitrogen tends to have a lone pair of electron, while this one acts as a nucleophile, so it will have a lone pair of electron, as well as the oxygen atom in a carbon monoxide molecule tends to have a lone pair of electron as well. So three of these are capable enough to act as ligand. The only one that does not have a lone pair of electron is this, is most probably an alkane, ethane, basically. Okay. Uh, Number two, it says an aqueous solution of transition metal ion absorbs frequencies of light corresponding to green, yellow, and red. Which ion is likely to be in the solution? Now we know the color of Mn2 plus is pale pink. It's pink, green, and that's blue. Now, according to this, green, yellow, and red, the colors which are not absorbed, according to VibGyor, it's basically the visible light, the seven colors which make up the visible light. So we can clearly see green, yellow, red. So we have green, yellow, red. The only things that have not been absorbed is blue, indigo, yellow, and of course violet. So something like, you can say that uh, the color is gonna be, it's gonna range from blue to violet or indigo, we can say, right? The color is gonna be something, within blue to indigo or violet, we can say. So that, because that's the whole thing, right? The color which does not get absorbed, that is the color which is transmitted by the transition metal ion. Now we can clearly see here that D down here is, the color is blue, and that is the most closest color that falls within this range with our deduction. So the answer would be option D. Moving on to group 3, we can clearly see the first 5 ionization energies of the elements have been shown. So the first question here is that, which are the ionization energies of a transition metal? Okay, transition metal, let's say. First of all, if we clearly see here that we tend to see a big jump between the first and the second ionization energy, which kind of indicates that there's only one electron in its outer shell, meaning that this metal exists in group 1, but we know that transition metal ions do not exist in group 1, so that will be out of the equation, out of our out of our list. Again, in option B, we can clearly see there is a big jump between the third and the fourth, meaning that there are 3 electrons that have been removed um, before there's a lot, before there was a big jump in the ionization energy, meaning that the fourth and the fifth electron has been removed from a higher quantum shell. So we can clearly say that this metal falls within group 3, while again we can clearly see here that between the second and the third, we see a big jump, meaning that 2 electrons were present in the outermost shell, making the metals to be present in group 2. So the only answer is option D. Okay, because group 1, 3, and 2 are metals which are not referred as transition metals. Moving on to the next question, they said here, of course, they said here that, what is the color of VO2 plus ion in the aqueous solution? Okay, first of all, what we would like to know is that the color of VO2 plus is somewhat what we know about related to our previous knowledge. So again, VO2 plus will never show green. It's not going to show violet and yellow. The only answer will be A, blue, because vanadium tends to show blue color. More specifically speaking, if we tend to find the vanadium oxidation number here, which is of course 2 plus 4, so that be vanadium 6. So vanadium 6 tends to have a color of blue. Okay, so yeah, sense, we can clearly see option A here. We clearly see that it says catalyst contains platinum. Now, this might be correct considering that catalysts do contain uh, consist of transition metal ion, and of course platinum is a transition metal ion. So and most of the transition metals tend to act as active catalysts, so this is correct. So that would be the correct answer. Now, if we see about B, C, and D, if we analyze option B, that both carbon monoxide and nitrogen dioxide are absorbed by the catalyst. Now, that will not be true because carbon monoxide and nitrogen dioxide are not simply absorbed. They basically react on the catalyst surface, of course, and then what happens is that the carbon monoxide is oxidized to carbon dioxide, and then what happens is that then of course the nitrogen dioxide also reduced to nitrogen. So kind of you can say that the catalyst facilitates the chemical reactions rather than just absorbing these gases. So yeah, option B won't be correct. It's more high chance the option B will be correct answer, but let's see option C and D. In option C, it says uh, after a reaction, the desorption of carbon dioxide and nitrogen takes place. Now, that is particularly correct considering the products, carbon dioxide and nitrogen, are formed on the catalyst surface and then they dissolve. Basically, they leave the surface to make room for new reactant molecules, right? Because that's the whole mechanism of the catalyst, absorbing the molecules, and then destroying the bonds between the reactant molecules and allowing new reactant molecules to get react together in order to and then later on dissolve the products. All right. Option D, it says it is a heterogeneous catalytic reaction. Now that might be true as well, considering heterogeneous catalysts involves the catalyst to be in a different phase, say for instance solid, from the reactants, which in this case would be gases. So yeah, that would be correct as well. So the only option that won't be correct is option B. Which of these pairs of elements are both transition metals as well? Uh, First of all, I won't say scandium. Scandium is not a transition metal because, of course, it does not tend to produce an incompletely filled d orbital. Its ion does not. It doesn't produce a stable ion, which tends to have an incompletely filled d orbital. So scandium is not considered as a transition metal. All right. If we talk about B though, gold and titanium, yeah, these might be correct because both of them are transition metals and they tend to produce stable ions with partially filled d orbitals. Moving on again, you can clearly see that CND involves zinc. Again, zinc's ion, Zn2 plus, it is a stable ion, but it does not have any partially filled d orbital in its electronic configuration. So the only option would be B. Again, number 7, it says what are the shapes of the complexes CuCl4 2 minus and PTNH3 2Cl2. Now, of course, we all know that CuCl4 2 minus would be a tetrahedral. Okay, so obviously A and B will become irrelevant when we tend to consider the options. Now, if I talk about this one, the platinum compound down here, this will be a square planar considering the platinum being the uh, central metal ion. We'll have the chlorine will be present here, while of course this is as it makes like this, while the nitrogen will be present somewhere here. So they are going to be present in a square horizontal planar. Either it might be a vertical or it might be horizontal. It might be horizontal or it might be vertical. Doesn't matter basically, but in a square planar, of course, the ligands tend to arrange themselves in a square, something like this. So C would be the correct option. Moving on, they said which is correct about stranded electrode potentials. Of course, if we see the options down here, there's a formula for this one down here. It says R ln K is equal to NFE cell divided by T. Now, we know that R ln K is nothing but del S total. So in a sense, what we can say, if the Faraday's constant, which is of course a constant, and I mean, sorry, this is the Faraday constant. That is the number of moles. So if the number of moles of Faraday is constant and the temperature tends to remain the same, so we can clearly see that the E cell down here is kind of directly proportional to del S total down here to del S total, as well as it's also proportional to ln k as well, considering r ln k corresponds to del S total. So B would be our correct answer. Okay, now moving on to the next question. They're saying 9a, which reagents are mixed with hydrochloric acid to produce benzene diazonium ion? Okay, now what happens is that if we talk about these right here, uh, sometimes we know that phenylamine is used. We know that phenylamine and of course sodium nitrite is used in order to produce this ion. Now, of course, this will be and this will be excluded, considering both of them consist of sodium nitrate, but we do not use sodium nitrate in producing benzene diazonium ion. So the only option we have relevant is A and B. Now, of course, we need to check out among these two. The correct option will be A, because if we reacted nitrobenzene, then the product would have been something else. We tend to mix phenylamine and sodium nitrite in a cold mixture, in a cold in situ mixture, in order to produce the benzene diazonium ion. So option A will be the correct answer. Moving on to the next part, it says that which reagents and conditions are used to prepare the yellow dye 4-phenyldenzyl-phenol from the benzene diazonium ion. Now, of course, if the conditions are already understood and already known, it should be 5 degrees Celsius. So, of course, A and B will be out of it, because if the temperature is 25 degrees Celsius is the temperature which is too high, the room temperature, and of course it won't react. I mean, the reaction will produce something else, not our desired product. So this leaves us to C and D, which both of them consist of cold mixture. Now, if we see in option C, uh, we do not actually mix phenol with acid, because the reaction won't take place with an acid. The only option will be option D, uh, where phenol is dissolved in alkaline solution with at a very nice cold temperature, which is 5 degrees Celsius. So this will also prevent from other substituted products from being formed, and our desired products will be produced at the end moment. So option D will be the correct answer. All right. Moving on, which sequence describes recrystallization? Now, if we analyze these options, now of course, before that, let's try to understand what's the recrystallization process. So this is the actual procedure as shown on the screen, that at first we dissolve the impure solvent in the minimum volume of hot solvent. Basically, the hot solvent allows us to dissolve more solute. Then we filter the hot solution to remove insoluble impurities, and then we cool the solution slowly, because this will cause the desired compound to crystallize out and produce more, while of course the soluble impurities remain dissolved. So at the same time, this will also cause more of our desired compound to be produced at larger amount. And of course, at last, we filter the cool solution to collect the pure crystals and remove the soluble impurities. So if we see in our first option down here, we can clearly see that option A says it is starting with a cold solvent rather than a hot solvent. I mean, the hot solvent is added later, but we tend to start it with a cool solvent. So it should be, so first of all, I mean, we basically tend to start with a hot solvent, not a cool solvent. So initially, it should have been the opposite. So yeah, that won't be the correct sequence, option A. If we see option B, uh, at first we can clearly see the it kind of dissolves the impurities in the hot solvent and then filters the soluble impurities first. Uh, so that is not even correct, because at first we filtered the hot solution to remove the insoluble impurities. So that's kind of inconsistent with the data provided down here. So that's not the correct order as well. So if we tend to see the next one, Option C, it says, of course, it says we tend to dissolve in a hot solvent, and then we filter the remove. Then we tend to filter the insoluble impurities, and then they're cooling it, and then they're removing the soluble impurities. Yes, that kind of matches with the provided data down here. So of course we can clearly say that C might be the most best order that basically describes crystallization in the best way. Option D is of course again incorrect because we can clearly see that after cooling, uh, the cooling basically removes the insoluble impurities. Now that's kind of wrong. It kind of removes the soluble impurities during cooling. The whole point of cooling the solution is to ensure that soluble impurities are removed. So of course option D will be relevant. So option C will be the correct answer. Okay. Moving on to the next one, they said here synthesis of aspirin from phenol is shown. So as you can clearly see, 11. Question is, what mass of aspirin is from 23.5 gram of phenol? Now, if you see this down here, uh, we are basically provided with the mass of phenol, and some theoretical yield is also provided, which is 80%, and the yield 75% is provided for step 2. So let us at first find the moles of phenol, which is much more easier to find. The molar mass is provided. So if we find the moles of phenol, that would be of course 23.5 divided by 94, so that would give us 0.25 mole of that of phenol. Now, if we calculate the theoretical moles of salicylic acid, at first we can use the mole ratio down here. So we can clearly see that 1 mole of phenol is kind of producing 1 mole of salicylic acid, which is the intermediate compound formed after step 1. So we can clearly say, since the ratio is 1:1, the moles of salicylic acid is also, 0.25 mole as well. Salicylic acid. All right. Now that we know the moles, we also know the yield, which is of course 80%. So that's the theoretical yield, right? So if you want to find the actual moles, so we can clearly use this. So the actual moles of salicylic acid produced would be, in reality, we can just do it, 80% of 0.25, right? So 80% of 0.25 is going to give us around, uh, that would be, of course, 0.20. So that's the actual amount of salicylic acid being produced. Now, again, we can clearly see if you use the same process, 1:1 ratio, the moles of we now know the moles of salicylic acid, which is 0.20 mole. So since the mole ratio of aspirin and salicylic acid is 1:1, so we can also say that based on the theoretical moles of aspirin, we can also say that, of course, the moles of the theoretical moles would be 0.20. Now of course our theoretical yield is also provided, which is 75%. So practically what we'll be getting is of course pretty simple. Let's find the actual moles of salicylic acid and aspirin. So the actual moles of aspirin would be, all you do is just find 7% of 0.20, so that would be of course 0.15 mole. All right, now we know the moles, and we also know the, of course, molar mass, so we can just easily find it out. Just multiply this with it. Eventually we'll be getting about 27.0 gram. So most probably our answer would be B. Okay, moving on, they say number 12 down here that an 8.4 gram sample of a hydrocarbon formed 26.4 gram of carbon dioxide in complete combustion. What is the molecular formula of this compound? Now, if we see uh, clearly that 8.4 gram is producing 26.4 gram of carbon dioxide. So if we write the reaction down here, that's 6CXHY plus O2, giving you XCO2 plus Y by 2 H2O. All right, now we know the molar mass of carbon dioxide is 44 moles, and we also know the moles of carbon dioxide, which we can easily find by using the mass and the molar mass. So the moles of CO2 would be 26.4 divided by 44. So that would be, of course, about 0.6. Okay, we know the moles of carbon dioxide. Uh, Now, each carbon dioxide molecule, of course, contains one carbon atom. So the moles of carbon would be the same thing, which is 0.6 mole. Right, so let's find the mass of carbon now. Mass of carbon would be, we know the molar mass of carbon, which is about 12, and mole as well. I mean, sorry, we need to multiply it. 0.6 times 12, so that would give us the mass of 7.2 grams. So we now know the mass of carbon. So what will be the mass of hydrogen? Well, the mass of hydrogen is pretty simple. We can just find the mass of hydrogen by subtracting it from the total sample mass. The total sample's mass is about 8.4 gram. So mass of H would be 8.4 minus 7.2. So that would provide us 1.2 gram. So now we know the mass of hydrogen, and we also know the mass of carbon. So if we know the ratio down here, CH, we can just do it. I mean, we can just easily find it. We can easily find the moles of hydrogen, which is of course 1.2 divided by 1, so that would be 1.2 mole. So we know the moles of carbon, which is 0.6, and moles of hydrogen, so we just place it down. 0.6 is to 1.2, and then if you just, of course, rationalize this concept, so that would bring us to divided by 0.6, that comes 1 is to 2. That means the empirical formula would be CH2. All right. Uh, Now, of course, if we analyze the options down here, will be incorrect considering it's the empirical formula itself provided. If we simplify this, we won't get CH2, so that's gone. Again, the same reason. If we do it, we get about CH3, so that's not correct as well. The only option is this. This is the most likely option of the molecular formula for this compound, option D. Because if we simplify this, C6H, we tend to get CH2. Moving on to next question. The next question says, what are the volumes of oxygen required and carbon dioxide produced at room temperature and pressure on complete combustion of 5.8 gram of butane? Now, everything is provided. At first, let us write the equation, which would be C4 H10 plus oxygen, giving us, of course, CO2 plus 5H2, H2O. So if you just balance it out, we can give 5, and then we can give here 4, and somewhere here this would be around 6.502. So this is balanced. Or you can just use instead of fractions, you can just use numbers as well. So if you use numbers, you can just multiply it by 2. So eventually you'll be getting 2. Uh, this will be about 13, and that would be, of course, 8, and that would be 10. So 8 and 10. Okay, so we know the molar mass is 58 gram per mole of C4H10O, so we can easily find its moles. So its mole would be, of course, you just divide it. We are provided with the mass, which is 5.8 grams, so 5.8 divided by 58.0, so that would be 0.1 mole of C4H10. Now, the next part here, if you use the stoichiometric, the whole reason why we wrote the equation here to understand the stoichiometric ratio, again, we can clearly see here that uh, this is the thing basically. So 6.5, or you can use this as well if you want. Okay, we can clearly see here the amount of oxygen required is 13. So we can see the ratio is 2 to 13, right? So we can easily find the moles. So the moles of oxygen required would be, that would be 0.1 times 13. So the answer would be somewhere around 0.65 mole. Okay, so if we move on to the next part again, uh, the moles of carbon dioxide produced, we can also find the moles of carbon dioxide. Because you can clearly see the ratio here provided is 2:8, so we can use that ratio and find it out as well. So that would be moles of carbon dioxide produced 0.1 times 8, not actually 8. Uh, 1 minute. Sorry, I made a mistake. That would be 13. So that would be 13 divided by 2. This will be, of course, 0.1 times 2 gives 8. 8 divided by 2. Sorry about that. So the answer would be, eventually, the answer would be 0.40 moles. So that would be the moles of carbon dioxide produced. Now, we can easily find both of their volumes. So for volume of oxygen, that would be, if you just multiply, we know that 1 mole provides 24 dm cube per mole. So I mean 24 dm per mole. So of course we can just multiply this with 24. Eventually you'll be getting around 15.6 dm cube, and of course this one's volume would be, just multiply 0.40 with 24. Eventually you'll be getting 9.6 dm cubed. So the answer matches with A. So option A would be the correct answer. Okay, let's say here the next question. What is the repeat unit, of course, of the water-soluble polymer ethanol? So we can see the 4 options down here: A, B, C, D. All right. Now, if we analyze these options, of course, option A down here, uh, option A is, of course, will be incorrect because we can clearly see polyethanol, right? So you can clearly see that there will be only one OH in each repeat unit. There aren't two OH present in ethanol. There's only one, so that would be incorrect. Again, if I talk about option D, the same reason, considering there are 4 OH provided, ethanol does not contain 4 OH. The same reason again for C. The only option that tends to have 1 OH is B. So B is the most likely repeat unit of the water-soluble polymer polyethanol. Okay. Now moving on to the next part, they said a repeat unit for a polyamide is shown. So this is the polyamide provided. The question is, which pairs of monomers makes this polymer? Okay. All right. Let's analyze the repeat unit first. From the structure, we can clearly see that the amide linkage is, of course, it would be this part down here, which is from here. This is the amide linkage, basically. I believe, yes, this is the amide linkage. Now, this kind of implies that, what do we see here? We kind of see here, from this, we can clearly see that the polymer basically comes from a diamine, which tends to have a 6-carbon chain. So the diamine would be what? The diamine would be something like this, CH26. So that would be the 6-carbon diamine. Again, if we see about another thing, this also implies, I mean, this part here implies what? This part implies that it's coming from a carboxylic acid, which has, of course, a 4-carbon chain. Something like this, HOOC, CH24COO8. So let's kind of get them. I mean, we can clearly see A consists of these options, so A would be the most correct answer, the best correct pair from this, which makes this polymer. Moving on, they say here 4 compounds W, X, Y, Z are shown. All right. So the question here, in key number 60, here, it said, which compound is an optically active amino acid? For an amino acid to be active, we'll be requiring a to be optically active, we will be requiring a chiral carbon center. Now, if we see these very clearly, do we have any chiral center in any of these options? First of all, this won't be correct because we can clearly see the central carbon is attached to 2 identical methyl group. The same reason for X. This will be the correct answer considering it has 4 different groups attached to it. So that is a chiral center, making it optically active. So option C will be the correct answer. Moving on, number B, which compound does not have the same number of peaks in the low resolution proton NMR and the carbon 13 NMR spectrum? Okay, first of all, if we analyze the compounds down here, the said here does not have the same number of peaks in the low resolution proton NMR. All right, first of all, if we see option A, compound W down here, what do we see here? We tend to get about we basically tend to get how there are basically how many environments. There are basically 1, 2, 3. There are, of course, there will be actually, sorry, there are actually 3 environments. One environment here, the second here, and these two are present on the same environment. So there will be 3 peaks, considering there will be 3 different environments in the low resolution proton NMR. And if we analyze the carbons down here, we can clearly see here that again these carbons will be in the same environment, while these two will be in different environments. So this is another environment, that's another environment. So again, 3 peaks in the carbon NMR as well. So they said here which compound does not have the same number of peaks. So we can clearly see compound W will have the same number of peaks, so that won't be the correct answer. Same will go for compound X because they're kind of same, so that won't be either. Okay. Uh, if I talk about compound Z, again, it kind of follows the same principle as compound W and X. So of course, D will have the same number of picks. The only option will be C, because if you see here clearly, we have 1, 2, 3, 4. So there will be 4 picks in the hydrogen NMR, and of course there will be 1, 2, 3 picks. Considering there will be 3 different carbon environments, so there will be 3 picks in the carbon NMR. So of course they won't have the same picks. Compound Y will be the correct answer. Again, they said asparagine is an amino acid. They said here what will be the structure of asparagine in an aqueous solution of pH 2. Now, if we resolve this, now if we analyze this, so we have 4 options down here, and pH 2 basically means that the structure of asparagine must show acidic properties. Now, according to Bronsted-Lowry theory, we know 2 things. An acid is a proton donor, a base is a proton acceptor. So, of course, the amine group here is the basic part, and it's supposed to receive the proton. Now, option A will be incorrect because it's not protonated. If we see B, C, D, 3 of them are protonated, but this is a zwitterion. Zwitterion tends to have neutral property, basically pH 7, considering it has lost. I mean, it's kind of amphoteric, considering it kind of accepts a proton as well as donates one. So it kind of acts as an acid and a base at the same time. So Zwitterion won't be the correct answer. If we see on C and D, we can clearly see that in option C, the amide oxygen was protonated, which does not take place in reality, considering oxygen is too tough to break and accept H plus. It has a double bond attached to it. So the only correct answer will be option D down here. Okay, now moving on to the next part. They say in a high resolution proton NMR spectrum and of asparagine, what would be the splitting pattern for the protons indicated by the arrow? So they're trying to say here, these 2 hydrogen atoms. Now, what does the peaks in a high resolution NMR represent? It kind of represents what? It kind of represents the number of hydrogen atoms attached to the adjacent carbon of that hydrogen environment, right? So if we clearly see down here, what do we see here? We tend to see there are 2 hydrogen atoms attached, all right? And we can clearly see that, of course, if we analyze this down here, we can clearly see that this carbon does not have any hydrogen atom, so attached to it. I mean, we do have we don't have any hydrogen atom attached to it, so we don't have to think about this. But if we see in this carbon, we tend to see that one hydrogen is kind of attached to it, the adjacent carbon, this one. So this kind of, we can use the n plus 1 rule, which says what? This basically, n is basically the number of hydrogen atoms attached to the adjacent carbon of the analyzed hydrogen environment. So we know that this one has 1, so 1 plus 1 would be 2. Basically, there's going to be 2 peaks in total in the high resolution NMR spectrum as S-ray gene, which kind of resonates to the option B, doublet. So doublet would be the correct answer. Okay, along with that, our section A is complete. Now let's move on to section B. All right, the first question here says that which species cannot act as a ligand in the formation of a complex ion? Now, if we see the 4 options down here, what is a ligand? A ligand is basically a species that tends to donate its lone pair of electrons to the central metal ion of the complex compound in order to produce that complex compound. Now, of course, we need to ensure which of these species consists of lone pair of electrons. So if we clearly see here, here's C and D. If you can see in D, we have a lone pair of electron at nitrogen, and we also do have lone pair of electron in a hydroxide ion, because hydroxide ions are normally, nucleophiles. And if I talk about B, carbon monoxide, it also tends to have a lone pair of electrons in it as well, which it will be able to donate to the central metal ion of a complex compound or a structure uh, in a in a to produce a compound. So the only option here is will be A, considering it has no lone pair of electrons. So since it has no lone pair of electrons, it won't be able to act as a ligand for the formation of a complex ion. So A will be the correct answer. All right, moving on to the next one. It says an aqueous solution of a transition metal ion absorbs frequencies of light corresponding to green, yellow, and red. Which ion is likely to be in the solution? Now, if you see here very clearly down here, now in order to solve this, if we clearly see down here that we can clearly see that 3 of the colors, green, yellow, and red, have been absorbed. So the colors which were not absorbed, we need to at first identify those. So that would be 3 colors, right? So according to Vibgyor concept, if we use that, it would be blue, indigo, and yellow. So we can clearly say that we know that from previous knowledge that the frequencies of light which are absorbed, that is not shown by the ion. It is rather the colors which are not absorbed that is shown. So we can clearly say that we're going to get a color. The ion is like in the solution is likely to show a color which is from blue, which ranges from blue to indigo. Okay. Uh, Now, if we now analyze these, A, B, C, D ions, Mn2 plus tend to show a pale pink color. So, no, that doesn't fall within this range. So that would be not the correct answer. If we talk about CO2 plus, it's pink. It tends to show pink. So, I mean, if there's no pink color in this range, so we're not going to include that as well. This leaves us C and D. Now, C is of course green, which leaves us CO2 plus blue, the nearest color within this range which has not been absorbed. So yes, D would be the most likely. In other words, CO2 plus would be the most likely ion in the solution. Okay, moving on, the first 5 ionization energies. Now, if we analyze these ionization energy values down here, A, B, C, D, you can clearly see in option A that we tend to see a big jump between the first and the second ionization energy, meaning that first ionization energy always tends to represent the number of electrons, the outermost electrons, the number of outermost electrons in a transition metal. So since we can see a big jump, that means only one electron was removed from the outermost shell. That means only one electron was present in the outermost shell. So we can clearly say that this metal is not a transition metal, considering it's in group 1, and group 1 metals are not transition metals. Moving on, if we see option B, we can clearly see a big jump between the third and the fourth electron. So that means 3 electrons were present in the outermost shell. Again, that makes the metal to exist at group 3, which again does not prove whether it's metal or transition or not, because transition metals are not found in group 3 as well. If we talk about C, we can clearly see there's again a big jump between the second and the third electron. So this kind of says that there are 2 electrons removed from the outermost shell. Again, making sure that this group is in group 2, this metal is in group 2. So obviously that won't be the correct answer as well, because transition metal ions do not tend to be present in group 2. So the only viable option would be option D. Moving on, what is the color of the VO2 plus ion in the aqueous solution? Now, if I talk about this one down here, we have VO2 plus. So first of all, this one's answer would be, of course, blue, because we know vanadium tends to show blue color in most of cases. Uh, I mean, green is for green is, of course, we have seen a little while ago, for Ni2 plus. Well, violet is for Mn for something else, for example, cobalt, while yellow is for something else as well, for chromium. Now, moving on, number 5, they said here, which statement about a catalytic converter used to reduce toxic emissions from internal combustion engines is not true? If I talk about this in more broad sense, all right, question number 18. The standard EMF of the cell was measured, all right, and this is the data provided, the electrode system in Fe3 plus. So the first question, they're saying that identify by name or formula the substances needed in the salt bridge right and half cell, with concentrations being included. Okay, so first of all, we'll be using one accurate substance, or one appropriate substance that can be used as salt bridge, we can say, would be concentrated solution of anything, maybe sodium nitrate or potassium nitrate, so any one of them will work. So concentrated solutions, KNO3 or NaNO3. The electrode obviously should be made up of something which is unreactive, so in this case platinum will work, or you could also use something, any other unreactive transition metal as well. Now of course the solution which will be containing, both of the solution must have a concentration of 1 mole dm cube, and as we can clearly see here that Zn2 plus and Fe3 plus ions are there. That means we'll be requiring solutions which will act as source of Fe2 plus and of course Zn2 plus. So what can we do? We can write solution containing compounds with 1 mole dm cube concentration of, you can say, maybe let's say iron 2 sulfate, FeSO4. Okay, and you can for Fe, there is obviously already Zn2 plus is present, so we don't have to, already it's mentioned, so we don't have to talk about it. So the solution C either might be 1 mole dm cube of iron 2 sulfate, so this will act as a source of Fe2 plus, or else you can also provide, you know or you can also give 1 mole dm cube of FeSO43. So whatever happens is that if you can provide any one of the solution, for instance iron 2 sulfate or iron 3 sulfate, which will act as a source, you will be able to get this reversible reaction in one way. All right, moving on to the next one. The question is, state why a salt bridge is used rather than a wire. Now of course, through a wire ions cannot flow, charges can flow, so using a salt bridge is basically a liquid solution, so ions will be easily to move ions will be easily uh, move from one place to another, and that is quite essential considering we'll be for performing the electrolysis here, because without the movement of the ions we won't be able to see the reading in the voltmeter, and we won't be able to measure the E cell. So we can say that ions can flow through a salt bridge but not through a wire. Now, they said here to write an equation for the reaction that would take place if the current was allowed to flow through the circuit, and of course, state symbols would not be required. So, if we clearly see here what is happening, the standard electrode potential, this is negative, right? So, since it's negative compared to its counterpart down here, so that means it's more likely to get oxidized. Okay, what does oxidation means? What? And this is vice versa, basically it's more likely to get reduced. So we all know this. Why am I saying this? Because it's negative. The more positive the standard electrode potential is, the more likely the species is supposed to get reduced, and vice versa. If it's more negative, then it's more likely to get oxidized. Now we know what does oxidation means: loss of electrons. So if that's the case, that means the equilibrium must be in the left hand side, while for this one the equilibrium should be at the right hand side, right? So yeah, if we do the math, now we can clearly see here there is a one Fe3 plus. So since Zn loses two electrons, each Fe3, that means at least 2 moles of Fe3 plus is going to gain each of these two electrons in order to produce 2 moles of Fe2 plus. So eventually, by using all our deducted knowledge, we can write the reaction as Zn plus Fe2 plus, sorry, 3 plus, and of course 2 moles, considering 2 moles of Fe3 plus are gonna gain 2 electrons being lost by Zn, and this will result in the production of Zn2 plus and 2 moles of Fe2 plus, as each mole gains 1 electron. So that will be the equation of the reaction. The next question, they said under standard conditions, what would happen to this value, if anything, when the Zn2 plus solution in the half cell is diluted? All right. So in this case, if it's more diluted, what's going to happen? Well, if it's more diluted, we know that the concentration is going to get decreased. So if the concentration tends to decrease, what's going to happen? Well, if the concentration decreases, the equilibrium, if we see this down here, this will be an equilibrium reaction. So what's going to happen is that the equilibrium will be, it's gonna move basically to the left hand side. So I mean, if the Zn2 plus is half diluted, so no, sorry, I think I made a mistake. If the Zn2 plus is half diluted, that means the concentration in this part decreases, so the equilibrium is going to shift to the right. So what's going to happen, we can write that as the Zn2 plus concentration decreases, the equilibrium shifts towards the right. All right, so that's a fact. So this will cause what? So this is gonna basically make the E cell more positive, considering what we know is that what is happening down here, the zinc is basically what, the zinc is basically becoming getting more oxidized. So obviously the E cell is going to be the E cell's value is going to increase, or in other words it's going to become more positive. So yeah, we can write down that the E cell value will decrease, or it's going to be will decrease. And of course we can say that uh, that's going to happen? Is it, or it become less it will decrease and it will become more positive? In other words, you can write that. Why is that the case? Because uh, you can clearly see here what is happening down here. This equilibrium is getting shifted to the right, because you can clearly see why is that's happening. The concentration of Zn2 plus is decreasing, so this is gonna get more negative. This value is gonna get more negative, right? And we know that the formula is E reduction minus E oxidation, right? So that's the formula for finding E cell. So if this thing, basically if the E cell oxidation, if this value becomes more negative, so in a sense, broad sense, we can say that this whole value is gonna get more positive. So that is why our E cell value will basically decrease, or it's gonna be more positive basically. Moving on, Grignard reagents, they are saying, are used to increase the length of the carbon chain, and this was the outline synthesis of propanoic acid from ethanoic acid is shown. Okay, so basically they said here what is the reagent and conditions for step one. So so we can basically use a reducing agent in order to solve perform this organic synthesis. So one nice reducing agent is lithium tetrahydroaluminate, with of course the medium being dry ether, because that's gonna basically ensure that water does not gets involved within the system. So that's the condition, and that is the reagent. For step 2, we can clearly see here that after the carboxylic acid has produced the alcohol, now in step 2 we can clearly see to produce compound X. How will we understand what compound X is? Now of course, if we clearly see in for Grignard in step 3, that in step 3 Grignard reagent was basically used, right? So if the Grignard reagent has been used, that means we can clearly say that compound X is a halogen alkane, because without the presence of halogen alkane, basically without the presence of a halogen in an organic compound, uh, performing it or reacting it with Grignard reagent is impossible. So what are so basically they're trying to say what are the reagents that are used in step 2 to convert this alcohol, this 1-degree alcohol, into an halogen alkane. So we all know that there are many ways. You can either use phosphoric acid with sulfuric, I mean mixed with concentrated sulfuric acid, or you can also use KBr. It doesn't matter. So if you use PCl5, you will be able to get the halogenous chlorine, or you can use bromine. So I'm just going to use bromine. It could be HBr or KBr. You can use any one of them. uh, I'm using potassium bromide with concentrated. Make sure that concentrated sulfuric acid, it is a necessity, because it's going to act as a catalyst. Now the so basically, if since I've chosen KBr, so my of course we can clearly see that there are two carbons, so the chain length does not increase, it stays the same. So only the OH basically uh, tends to get substituted by the halogens. So obviously it would be C2, 1 2 3, there are 5 hydrogens, so C2H5. And since I used KBr, so we'll be getting Br. The another bromine atom tends to produce hydrogen bromide as a gas. In step 3, the reagents and the conditions, since they basically said Grignard reagent, before we tend to react something with Grignard reagent, we tend to at first add magnesium and ensure that the halogen tends to get we ensure that the halogen tends to get you know substituted by the magnesium. So we take magnesium, and of course again dry ether as a condition, so that again water does not get involved in the medium. And now the formula of the Grignard reagent, we can give any we can give any. Now since how to ensure the formula of the Grignard reagent, see clearly that we have two carbons here, right? So since there are two carbons and 5 hydrogens, so we are just gonna keep this as it is, like CH3 CH2 gone. Now we are gonna give X here. Of course, sorry. Mg, obviously because we added in step 3 the magnesium, like I said. Now we can give X here because we don't know which halogen can be used, because we can use any halogen if we want, as any suitable halogen will work basically. Okay, because at the end of the day the X is gonna get the X is going to get, you know, removed as a byproduct from, you know, in the in the as the with the at the end reaction. In step 4, we can clearly see after the Grignard reagent has been added in step 4, in order to convert this into propanoic acid so that this X goes away. So what we do is that we basically perform hydrolysis. So this hydrolysis will cause the, you know, the hydrolysis will basically cause the carboxyl group to get added, and the magnesium and the halogen to get removed or discarded from the main compound. So we can write as, you know, we can basically use dry ice. We can use dry ice because that will act as a good source of water, and then we can then basically hydrolyze it and hydrolyze. We can basically for use it for hydrolysis. So that would be the reagents for, you know, performing step 4, to convert the intermediate ion, the intermediate product produced by a Grignard reagent into the main product, which is the propanoic acid. The next question says, the question is about some chromium compounds, as you can clearly see. So this whole synthesis has been provided. So they told us that to write an equation for reaction 1, uh, by reaction 1 what we mean to say is this one right here. So Cr3 plus being converted to Cr2O72 minus. So if you use the data booklet, hydrogen peroxide has been used. So our reactants are pretty simple. It's just Cr3 plus. Since state symbols are not required, I'm not providing the state symbols. H2O2. Now, of course, what is happening down here? An oxygen is getting added, and normally we tend to basically use water in this case, because uh, if you want to convert something, water is required. So basically if you want to convert chromium into Cr2O72 minus, and according to the data booklet water is provided, so do check it out. So now, since of course, since this is a we can clearly see, so eventually what is produced, Cr2O72 minus is produced, along with, of course, since I've added water, H plus. Now we can just balance it out with 8 H plus, and this will obviously be 3, and since there are 2 chromium, so 2 Cr3 plus. So this is how you balance the equation. Again, they said here that Cr2O72 minus reacts with a metal called M in acidic conditions, forming something called Cr3 plus and metal. So the metal basically loses 2 electrons to produce an M2 plus cation. So what can we say about it? That we can clearly say that maybe the metal is from group 2, considering group 2 metals tend to lose 2 electrons. Maybe it's from maybe it's a transition metal such as vanadium, or it could be a non-transition metal such as zinc. Either way, any suitable metal which tends to lose or has the capability to lose 2 electrons. So if we check out the E cell value, there are many. So if we judge using the data booklet, so there are many. For instance, there is magnesium, vanadium, and it could be zinc, it could be iron, it could be nickel, it could be copper, it could be, anything, to be honest. So uh, using this, if we, analyze it, let's say we basically want to calculate, let's say the metal is magnesium, let's say. All right, so according to the data booklet I can clearly see here that the E cell value would be, for magnesium, would be, of course, 3 point plus 3.7 V, considering it's more likely to get reduced, sorry, it's more likely to get oxidized. So that's why, basically. All right, moving on to the next one. Give the formula of the species responsible for the purple color formed in reaction 3. So we can clearly see that in reaction 3, a purple aqueous solution is produced. So whenever we add aqueous ammonia to a transition metal, a complex compound is getting produced. Now, since excess ammonia is added, so what is happening here? So the ligand, we will get to see complete ligand exchange. So the color for purple would be obviously, it would be for CR3, I mean it will basically be this one. So if you do complete haulage, so it will be CrNH3, since ammonia is added, 3 6 of the ligands basically get replaced, so eventually you will be getting something like this. Now ammonia does not have any charge, so the only charge that will be is P of the central metal ion, which is chromium 3 plus, as shown right here. So that would be the answer. And the type of reaction would be obviously ligand exchange, because when we add uh, excess aqueous ammonia, ligand exchange takes place rather than hydrogenation or protonation reaction, because that's what happened when you do not add excess ammonia. Now question is, state whether or not the reaction in reaction 4 is a redox reaction. And to justify using oxidation number, it's pretty simple. As you can see here in reaction 4, what is happening? uh, the Cr2O7 2 minus is getting converted to CrO4 2 minus. Now if you check out chromium's oxidation number right here, it will be 2x plus oxidation number of oxygen is 2 times, sorry, 7 times -2 is equal to the whole one is of course -2. So eventually you'll be getting x as -2. I mean, this is about +6, I believe. Yeah, eventually you'll get x is equal to 6. So basically chromium's oxidation number is +6. If you calculate in this one as well, the chromium substitution number, it's x plus -2 4 is equal to -2. So again it's +6 if you do the math. So we can clearly see that the oxidation number is not changing, even though the color is changing. The oxidation number of chromium is not changing, so it is not an oxidation number, considering no oxidation takes place, because for a redox reaction to take place, both oxidation and reduction are supposed to take place simultaneously. So it's not redox because the oxidation number has not changed. uh, since chromium's oxidation number is +6 for both, in both Cr2O7 2 minus and CrO4 2 minus. Okay, so it's kind of same for both. The next question, they said here that deduce the simplest formula of this double salt. Now for double salt basically means that uh, 3 of these ions are involved. So if you want to include something, so I mean the ions could be of any order, so you can just give K and then Cr and SO4 if you want. So it's, let's just give K and of course Cr, and we have SO4. All right, so yeah, eventually you'll be getting something like this. So that is the simplest formula of this double salt. Now, moving on, the question said here that double salt also exists as hydrated crystals. When a sample of the hydrated double salt is heated until all the water of crystallization is removed, so we have 56.74% of the original mass of solid remains, they said here. So they told you to calculate the number of moles of water of crystallization in 1 mole of the hydrated double salt. Basically, they're telling you to find the value of X in the hydrated salt. Alright, so let us at first calculate the molar mass of the double salt, which we have written here. So it's pretty simple, right? The molar mass of KCr SO42 would be, we know this is 39.1. For chromium it's 52. Now since everything is times 2, so you can just basically plus 2. We know for sulfur it's 32.1, For oxygen, it's 16 times 4. Eventually, the total value will be 283.3 gram per mole. That's the molar mass of KCrSO2. Now, we can easily find the moles because we know the mass provided, which is 56.74%. So the the moles of KCrSO2. We know the molar mass, which is 283.3. Mass by molar mass provides you the moles, so it's pretty simple out here. Eventually, you'll be getting about 0.200 mole of KCrSO2. Now, we also need to know the moles of water because that's very important. Now, since it's provided in percentage, that means the total original mass was 100%, out of which 56.74% was left. That means the rest got evaporated as water. So the moles of water would be pretty simple. What you can do is that you can get the mass, just subtract it, 100 minus, of course, we have 56.74, right? That's the amount of water that got evaporated. And now that's the mass, right? So if you want to find the moles, you just divide it with it's with the molar mass of water, which is of course 18. So eventually 18 equal to, this will provide you 2.403 mole. All right. So now you know the moles of KCrSO2 and also the moles of water. If you just divide both of them, you'll be able to get, basically you divided the moles of water with the moles of KCrSO4. So ratio will provide you the value of the number of moles in 1 mole of hydrogen salt. So in 1 mole, this would be, just divide 2.403 divided by 0.200. So if you divide it, eventually you'll be getting 12. So it's basically 12 moles of water crystallization in 1 mole of the hydrogen double salt. Okay, the value of X is 12. Again, they said we require small amounts of chromium 3 ions in our diet. All right. So the next question here is that show by calculation the concentration or the CR3 plus level in this blood sample exceeds the safe limit. Uh, that's basically the safe limit provided. That means it should be less than 4 parts per billion. Okay, we can do it in many ways. At first, we can just calculate. At first, let's do this. Clearly see mole per dm cube is provided, right? So we can easily convert this into gram per dm cube first. So how can we do that? You just basically multiply this with the molar mass of chromium. So that would be, if we do the math, because 1.345 times 10 to the power negative 7 times 52. Now if you see why I did it, because if you see here, mole per dm cube times 52 gram per mole. So the mole gets cut, so it's just gram per dm cube. Eventually you're getting 6.994 times 10 to the power negative 6 gram per dm cube. The reason why I did that, because now if we divide this with of course 10 cube, we'll be able to get gram per cm cube. Let's convert this into gram per cm cube. So if you just divide it by 10 cube, eventually, sorry, not 10, yes, 10 cube. So eventually you will get 6.994 times 10 to the power negative 9. You just add them up. Negative 9 gram per cm cube. The reason why I did this, because you can clearly see here that 1 billion is what? 1 times 10 to the power 9. Okay, so we basically want to get parts per billion, so we can just multiply this with of course this one down here. Since they said here to assume 1 gram per cm cube, to assume the density of blood to be 1 per cm cube, that means 1 billion represents 1 gram times 10 to the power 9, 10 to the power 9 gram per cm cube. So you can just multiply this with of course 10 to the power 9. So eventually what you'll be getting, you'll be basically getting about 10 to the power 9. So again, this get cut, so eventually you'll be getting 6.994 ppb parts per billion. Now that's way above the safe limit, So yes, it kind of exceeds the safe limit. That's correct. So we have shown this correctly. Check this out. EDTA4 minus has been considered a potential treatment for CR3 plus poisoning. So they're told here to suggest how EDTA4 minus would act to treat CR3 plus poisoning, giving a reason why EDTA4 minus would be preferred to other reagents such as 1,2-diaminoethane, this one. Now, we have to check this out in many ways. First of all, EDTA4 minus is a hexadentate ligand. That means it can produce what? It can basically produce 1, 2, 3, 4, 5, 6. It can basically produce 6 dative covalent bonds, considering it has 6 lone pair of electrons. All right. Now, uh, compared to 1,2-diaminoethane, you can clearly see it has 2 lone pair. It's a bidentate. Um, it's a bidentate ligand, so considering it can produce 6 dative covalent bonds, this complex is more stable than a bidentate one, than the complex which consists of a bidentate ligand. All right, so this is very important. So basically, due to stability, uh, EDTA4 minus is more preferred. So at first, let's write that EDTA4 minus is a hexadentate ligand, so it can produce 6 dative covalent bonds. As a result, will be more stable. So since it's more stable, it can, for which it can easily, you know, trap or remove CR3 plus. Trap and remove CR3 plus from blood. Now that's very important because the more stable the complex is, the more ability it has, to trap CR3 plus within the complex and to hold it for a long period of time before it gets removed from the body. So that is why EDTA4 minus is more preferred due to its stability, and and the stability basically comes due to the nature of its nature of the ligand, which is it's a hexadentate one. All right, the next one, question number 21, they say here, the electronic configuration of iron is provided. So you just have to write the Fe2 plus 1. So if we basically use the Holmes rule, everything is same. It's just like the previous one. Now, since 2 electrons are removed, remember that 2 electrons are at first removed according to the Aufbau principle from the lower energy orbital. And of course, 4s is lower one than 3d. So obviously, from here, 2 electrons will be removed. And after that, so everything is going to remain the same. It's just that this will remain empty. Okay, moving on, an aqueous solution of iron 2 sulfate is pale green in color. This is very important. The pale green is coming from the iron 2. When it is left exposed to the air, the solution turns brown. Why it turns brown? Because obviously the iron 2 here, Fe2 plus, gets oxidized. It basically, the air tends to oxidize Fe2 plus to Fe3 plus, because we know what is happening. Oxidation is what? Loss of electron. So it's going to lose more electrons and produce Fe3 plus. Now Fe3 plus is a different color. It is brown. So that is why the pale green color of the solution turns brown or brownish. And white forms, like, why does this form? It's because Fe3 plus in nature is more stable than Fe2 plus. The reason why is pretty simple. If you see down here, uh, Fe2 plus's electronic configuration is something like this, but if you want to write the electronic configuration of 3 plus, what happens? uh, Same case, but it's just that one electron goes away. So now why Fe3 plus is more stable, considering, because it's basically partly due to, you can clearly say, sorry, I think what happens is that in Fe3 plus, what happens, sorry, 1 minute, the electronic configuration is something like this. So one of the electron moves away from here, from this orbital down here. So we can clearly see that the electronic configuration of Fe3 plus is what? It's more half filled, meaning that it's more stable than its counterpart Fe2 plus. And anything that is more stable, it's going to stay there, and the reaction is going to be more favorable. That's why this color change is seen. So we can say that the oxygen in the air oxidizes the Fe2 plus, forming the brown Fe3 plus. Now Fe3 plus is more stable than Fe2 plus due to its half filled d orbitals within its configuration, making it more favorable to get produced when left exposed to air. Alright, moving to the next part, they say that many moss killers contain iron 2 sulfate as the active compound, and potassium manganate 7 can be used to determine the amount of iron 2 sulfate produced, and everything values has been provided. So the first question they say here, calculate the percentage by mass of iron 2 sulfate in the moss killer, and to provide your answer in an appropriate number of significant figures. At first, let's calculate the moles of MnO4 minus, right? Because we are provided with the concentration, and I believe we're also provided with the titer. So how much basically reacted we know. So let's calculate the moles of MnO4 minus in the titer. Moles of MnO4 minus, because that's the thing that comes from the potassium manganate 7 solution. So that would be, of course, we just basically multiply the volume with the concentration. That would be, now since this is cm cube, just divided by 1000 times the value is 0.00740. Eventually you'll be getting 1.3098 sorry, times 10 to the power -4 mole per dm cube, mole basically, sorry. So that's the mole of MnO4 minus. Now check that. So from the 250 cm cube, 25 cm cube was taken, right? So now when we do calculate the moles of Fe2 plus, obviously the, you know, in the solution, now we clearly see the mole ratio is 5:1. So we can use this mole ratio to calculate the moles of Fe2 plus. So 5:1 ratio, like 5 moles of Fe2 plus is reacting with 1 mole of MnO4 minus. So the moles of Fe2 plus in, remember, 25 cm cube, in 25 cm cube, we are basically calculating the moles of Fe2 plus in 25 cm cube solution. So that would be 1.3098 times 10 to the power -4 times obviously 5 moles, because that's the ratio. So eventually you'll be getting what? Eventually you'll be getting as 6.549 times 10 to the power -4 moles. So that's the mole of Fe2 plus in 25 cm cube. Now we want to convert this 25 cm cube into a 250 cm cube solution, because that's where the whole thing is, right? So if we multiply 25 cm cube with 10, that means we need to take 10 portions of 10 25 cm cube solutions of containing Fe2 plus in order to produce 250 cm cube of the solution of iron 2 sulfate, right? So we can just multiply 10 solutions, each solution will contain 6.549 times 10 to the power -4 mole of Fe2 plus. So we can clearly find the moles of Fe2 plus in 250 cm cube. All you do is just multiply with 10. So that would be -3 times 10 to the power -3. It's just simple math. Now we can now calculate the mass of FeSO4 because we know the Fe2 plus mode. So the mass of FeSO4 would be, we know the molar mass which has been provided, so we can easily find the, and the mole we know, so you can just multiply with the molar mass 151.9, so eventually you'll be getting about 0.9999479 grams. So that's the mass, actually 479 grams. So that's the mass of FeSO4. So they said here to calculate the percentage by mass of iron 2 sulfate, right? So we can clearly see here that's the percentage, that's the total amount provided, right? And that's the amount that reacted. So we can basically find the percentage by mass of FeSO4. Total mass is of course 6.42, out of which the percentage of FeSO4 was 0.99479 that reacted, so times 100, you'll be getting about 15.495%. So that's the percentage of FeSO4 present in the molecular. Okay, so that's how it goes. All right, moving on. Suggest why iron 2 sulfate is acidic when dissolved in water. First of all, uh, this is a little bit tricky question. So first of all, what do we have here? We have a transition metal ion called iron. So when the iron tends to get surrounded by water, which water molecules, which itself is a ligand, it tends to produce an aqua complex, or you can say something like this. So we can write that when Fe2 plus ions get surrounded by water molecules, it tends to produce a complex called hexaaqua hexa hexaaqua iron 2 complex. So something like this, FeH2O6, right? Now the main thing is that, uh, what do we know about the, according to the Bronsted-Lowry theory, what do we know here? We know, according to Bronsted-Lowry, that acid is a proton donor, right? So what happens is that, uh, as this happens, the Fe2 plus ions loses the protons, its protons, to the water molecules. Okay, so deprotonation takes place basically, right, to the water molecules. So something like this reaction takes place, you can say that. uh, so basically, after the complex gets produced, it kind of dissociates to produce something like this. The proton, one of the proton, tends to get, I mean, one of the proton is taken away from the water molecule. So this is what happens: H2O5, one of the H plus gets away, and while the OH remains, right, forming a plus, because OH minus and Fe2 plus, so 2 minus 1 is just plus 1, with 1 H plus coming out as a byproduct. So what is happening here? It's donating a proton via the process called deprotonation reaction, as it detonates, right? Dissociates. So we can clearly say that our, according to the Bronsted-Lowry theory, so FeSO4 is acting as an acid according to this theory down here. Okay, so that would be your answer. All right, the next question they said here: compare and contrast the bromination of benzene and the bromination of phenolphthalein. These two are different, synthesis systems that we need to analyze greatly. Now, fun fact is that since both of them involve an aryl compound, so the first similarity we can say would be both reactions are electrophilic substitution reactions. So that's the mechanism that follow both of the reactions, considering both of them have aryl compounds such as benzene and phenol. Now, of course, the key differences, let's start with the differences. The key differences are pretty simple. First difference, of course, the products. The products are different. So in the case of benzene reacting with bromine, if you write the reaction, so what happens? The benzene basically reacts with Br2, producing something like this, Br plus HBr. All right, so that's the first reaction. So what happens if now phenol reacts, when phenol reacts uh, with OH provided, we know that. So what happens? Tribromo hydroxybenzene is produced, something like this. Okay, phenol's there though. 3 HBr in order to balance it out. You clearly see down here there will be 3 as well. Yeah, so we can clearly see the product, the difference in the products. So that's a difference. Now one thing's pretty clear. Another difference is that we can clearly say that benzene, of course, requires a catalyst, right, or a halogen carrier such as ELBR3, or you can say FeBr3 with heat, of course, because it will allow the reaction to initiate. And on the other hand, the condition for bromine is that, for phenol, is that phenol reacts with bromine water at room temperature at 25 degrees Celsius. So you won't be requiring any halogen carrier in this case. Lastly, we can clearly say that phenol is more reactive in the sense than benzene because it has lone pair of electrons on the oxygen atom. All right, there's lone pair of electrons on the oxygen atom, um, and which tends to get delocalized, right, into the ring, making the phenol more susceptible to an electrophile attack. So basically they're trying to say is that our OH here, this oxygen here, has a lone pair of electrons, which it donates, basically it gets delocalized and it get donated to this benzene aryl ring down here. So as as the aryl ring tends to receive it, it becomes more susceptible and more reactive towards an electrophile when it approaches towards it to attack. So that is why phenol becomes more reactive. It's kind of more it kind of makes phenol more reactive compared to benzene, which does not have any delocalized electrons within its ring. That kind of provokes more bromine towards it. So these are the differences basically.
Are you still stuck in chapter 1? Well, your exams are racing closer. You have watched thousands of videos on YouTube, but your marks are not moving. It's not you, it's the method. Let's fix it. Welcome to Exam Essentials, where every second counts and every session hits. You have seen our question solving walkthroughs, right? Now it's time to go all in. We offer two signature courses for A level and O level students. The first one is the High Impact Crash Course, which is basically launched 5 to 6 months before every exam session. Whether it's May 26, October 26, or any future sessions, this course is your fast track to results. For the upcoming October 25 and the January 2026 sessions, our high impact crash course will be starting from June 1. So, book your seats as soon as possible. Now, the second course that we always offer is the complete 1 year course designed for students preparing for May 26, October 26, January 2027, and beyond. To know more, check the description box or message us directly on WhatsApp or on our Facebook page, Exam Essentials. Stop struggling, start scoring. You have seen us on YouTube. Now it's time the world sees you succeed. Your top grade is waiting. Let's go get it together.
Okay, with this, our section B is complete. Now let's move on to section C. Okay, in question number 23, they're saying that procaine is a local anesthetic that was commonly used until the end of the last century in dental procedures to numb the area around a tooth. So they said here to use the molecular formula of procaine. Now, of course, the displayed formula has been provided down here, so it's gonna be very easy. So we have 1, 2, 3, 4, 5, 6 carbons, 7, 8, 9, 10, 11, 12, 13. So there are 13 carbons. If we tend to count the number of hydrogens, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Then of course you have 15, 16, 17, 18, 19, 20. So there are in total there are 20 hydrogens. So H20, we have 2 nitrogens and 2. Then if we talk about oxygen, we do have 2 oxygens down here, so that's O2. So this will be the molecular formula of procaine. Now, moving on to the next question, B. Possible reaction sequence to make procaine is shown. So this is the possible reaction sequence down here. So the next question, they're saying that identify by name or the formula the two reagents required for step one. Uh, in step one, we can clearly see what is happening down here. You are basically doing methylation. We're basically adding methyl. So halogenation. So halogenation of benzene involves one of the reagents to be an halogen alkane. So in this case, of course, since a methyl group is added, so we'll be using the halogen alkane chloroalkane. So this will be one chloro methane. So or we can give one, I mean, since this is, we can use one chloro methane, or we can also use one bromomethane, whatever the halogen is. So I'm using one chloro ethane methane, sorry. And of course, the another thing that will be required, the halogen carrier, could be, since we used chloromethane, so we'll have to use aluminum chloride. If you would have used bromine bromomethane, then it would have been iron 3 bromide, or iron or aluminum bromide, whatever that is, depending on the halogen alkane you take for step 1. Okay, moving on to the next question. There's said here for step 2, to draw the mechanism for the reaction, including the formation of a suitable electrophile and the regeneration of a catalyst. Now, of course, this will be electrophilic substitution reaction. So at first, the first step is pretty simple. So what happens is that, so we do have the methyl group in step 2, right? This is the methyl group in step 2. So it tends to produce 1 2 3 4 1 4 methyl nitrobenzene. So we can clearly say, um, so at first what happens is that the electrophile attacks. Obviously the electrophile is supposed to attack the aryl benzene ring here, considering it consists of delocalized electrons and it's negatively charged. Now, in the next stage that happens is that the one of the hydrogen atoms break down like this. So this tends to produce uh, unstable carboc, it's a complex, unstable ortho complex, something like this. Okay, and then you have H, right? So now the hydrogen tends to donate one electron to this unstable aryl arene, and then at the third step, what happens is that the hydrogen atom goes away. resulting in the production of a stable compound called methyl nitrobenzene. So that's it. Something like this, with the H plus coming as a byproduct. So this is the mechanism of the whole reaction. So you'll notice one thing, that is that they're also said here to show the regeneration of the catalyst. So what did we use here? We basically used nitric acid. What did we use here? We basically used nitric acid along with concentrated sulfuric acid. All right. So the reaction that's gonna take place at first is that the nitric acid is gonna react with H2SO4, resulting in the production of our very nice electrophile, which tends to attack the arene ring along with hydrogen sulfide, SO4, and water. Now, of course, we'll be requiring the regeneration of the H2SO4. So again, what happens is that the HSO4, the plus, I mean, sorry, minus. So what is happening here? The H plus, which has been produced as a byproduct, as it got broken down from the original reactant, it tends to react in a secondary reaction, resulting to the production of H2SO4 again. So that's how you tend to show the whole reaction and the mechanism. Okay. Moving on to the next question, they say here for step 5, name the type of reaction and of course, and draw the skeletal formula of the reagent needed to carry out this reaction. Now, if we clearly see in step 5 down here, what is happening? We can clearly see an ester group is getting added up. That means the reaction will be esterification. And of course, if we judge from they said here, the skeletal form of the reagent, if we judge from the provided product down here, clearly we can see that this part will be our reagent. So basically what is happening down here is that the H basically went out. This part is basically the alcohol part. So what happened here is that the H part from the OH went away. So we're just going to add H with this here, and that's how the reagent will be formed, because we know that basically a carboxylic acid and of course an alcohol reacts together to produce an ester traditionally. So yeah, so the type of reaction will obviously be esterification, and of course it will be skeletal formula, as I said. O is going to be something like this, right? The rest of the structure of the reagent remains the same, just as it was given previously down here. All right, moving on to the next question. The reagents required for step 6. They told you to identify it. Again, in step 6, we can clearly see that this is getting converted into an azodide. So, of course, the reactants required for azodide is, of course, an in situ mixture of tin, right? Tin and concentrated hydrochloric acid at 5 degrees Celsius. We need to mix concentrated hydrochloric acid. So these are going to be the reagents for required for step 6. Now the next question, they say here that procane contains 2 nitrogen atoms, right? Procane contains 2 nitrogen atoms, one of which is a stronger base than the other. Okay, explain why the basicity of the nitrogen atoms in procane is different. All right, if you see here clearly, the alkyl groups attached, you can clearly see 2 alkyl groups attached to the nitrogen atom down here. Now these alkyl, we know that alkyl groups are electron donating, right? So these are electron donating. But if you see this one down here, the nitrogen which is attached to this bending, which is basically which is connected with the benzene ring. Now this benzene ring is what? This is basically electron withdrawing, right? Considering it already has delocalized electrons within it, so it is supposed to withdraw, since we know that like charge is ripple. Since we know that like charge is ripple, so it is supposed to withdraw any other electrons that gets incorporated into it. So basically what we're trying to say is that whatever electrons are provided, they will tend to get delocalized. All right. So now if we see clearly down here, we know that base is of course proton acceptor, because if we see here clearly, since these are electron donating. So if they donate their electrons, so they will have a greater chance to express their basicity, considering you know, they'll have more chance to um, to accept and attract a proton, considering electrons are getting out from them. So that's why we can clearly explain the difference in the basicity between this part and this part. So of course the basicity of the alkyl nitrogen down here will be greater than the basicity of the benzene amine, or the nitrogen here. So we can write that alkyl groups attached to the nitrogen are electron releasing, right? While the benzene ring attached to N is electron withdrawing. Okay, so as a result, the basicity of alkyl nitrogen greater than the benzene one, because it has more chance to accept protons. We know that acid is a proton donor while the base is a proton acceptor. So since the nitrogen in the alkyl nitrogen tends to have a greater chance of accepting protons, so that's why we can easily say that it will tend to show a greater level of basicity compared to its counterpart down here to accept the protons and form dative covalent bonds. All right. Next question, they say it here, procaine hydrochloride is made by reacting procaine with hydrogen chloride in a 1:1 ratio. All right. They told you to draw the structure of procaine hydrochloride, showing how the hydrogen ion attaches to the molecule. All right. You can clearly see down here that uh, this is procaine. You can clearly see this is procaine down here. This is procaine. So what's going to happen if we tend to, you know, just copy paste this part down here? So what's going to happen? This is procaine. So what happens is that here the nitrogen atom is going to donate some of its lone pair of electrons to the hydrogen atom down here, and of course what happens is that since the at first what happens is that the hydrogen tends to come from HCl, so obviously the HCl bond is going to break down, and then this will result in the production of Cl minus, of course, and the hydrogen down here. Now, since hydrogen has an empty orbital and we tend to have a lone pair of electrons in nitrogen, so what's going to happen? It's going to donate its lone pair of electrons to the empty orbital of hydrogen, and this will result in the production of a dative covalent bond. All right, this will result in the production of a dative covalent bond, and that's how the hydrogen attaches to the procaine hydrochloride molecule. Okay. Next question, they said here, explain why procaine hydrochloride is more soluble in aqueous solutions such as blood plasma than procaine. First of all, this kind of makes this kind of makes procaine hydrochloride ionic. All right, because due to the deficiency of electrons, why there is a deficiency of electron? The reason why plus has been provided because the lone pair of electrons has been donated to the empty orbital of hydrogen. All right, so that is why a deficiency of electron has been created. Now, since this has caused the whole molecule to become ionic, and we tend to know that in water, the ion dipole interaction plays a huge role for compounds to dissolve in water. So, so what happens is that procaine hydrochloride can write becomes is an ionic compound, ionic molecule, and so the water molecules tend to interact as ion dipole, interact like ion dipole interactions, causing the molecule to hydrate. So what happens is pretty simple. Around the plus and of course around the negatively charged down here, what happens is that uh, the negatively charged oxygen atoms tend to surround the positively charged nitrogen down here, while the positively charged hydrogen atoms tend to surround the uh, negatively charged nitrogen atom down here. So that's how the ion dipole interaction takes place, which results to a huge amount of energy being released, known as the enthalpy change of hydration. That results to the protein hydrochloride to be more soluble in aqueous solutions. All right. Now, the next question they said here that procaine nowadays has been replaced by lidocaine, okay, which is a related compound as a local anesthetic in dentistry. Okay, a lidocaine is applied to 2.2 cartridges that contain 44 milligram of lidocaine. A typical adult dose is 1.5 cm3. So they told you to calculate the number of molecules of lidocaine present in 1.5 cm3 dose. Okay, at first let's calculate the mass of lidocaine in 1.5 cm3. Mass of lidocaine in 1.5 cm3. Since that's the typical adult dose, so we know a lot of stuffs here. At first, we know the volume, all right, and we also tend to know this one down here, um, 2.2 cm cube, right, and this is the mass, right. So we can easily do it. Now we can convert this mass into gram, which would be 44 divided by 1000. So that would give us to 0.044 gram, right? Okay, so we can easily find the mass of lidocaine in 1.5 cm cube. So since the total mass is 2.2, so out of 2.2, so that would be 1.5 divided by 2.2 times 0.044 out of the 44 milligram of lidocaine. What's the value? So that would be 0.03 gram of lidocaine in 1.5 cm cube. Now, since we know the mass, we can easily find the mole. So the mole would be 0.03 divided by the molar mass, which is about 234 gram per mole. 234 gram per mole, right? So that's basically around 1.2821 times 10 to the power negative 4 mole. So now we know the moles, so we can easily find the molecules of lidocaine since we know the Avogadro constant, which is about 6.02 times 10 to the power 23. So of course, the molecules of lidocaine, since 1 mole is 6.02 times 10 to the power 23, so of course this much amount of moles would be, you just multiply 1.2821 times 10 to the power negative 4 times 6.02 times 10 to the power 24, actually 23. So our answer will be about 7.7179 times 10 to the power 19 molecules. So that's the amount of lidocaine molecules which are present in 1.5 cm of adult dose. Okay, so with this, our paper is complete. We hope to meet on an exciting new video in the future. All right, I hope you enjoy it, and I hope you have enjoyed this whole session. And of course, don't forget to like, share, and subscribe. Bye bye.